Okay, physical science time. Today, as we often do, as we probably will for the rest of the semester, we are talking about matter, but today we're talking about the different arrangements. I mean, I guess that's a pretty good title. Arrangements of matter. I think that's a good title, and I'm going to tell you why in a second. But first, let's write down the objective, which is explore the cause and effect relationship among states of matter. Explore, that makes it sound like you're going to explore things, like Dora the Explorer. Not a sponsor. Other children's TV shows are available. Explore, now that I've said all that nonsense, I forgot what the rest of it was. Explore what? I can't see it from here. Would someone please tell me? Well, hold up. The cause and effect relationships among states of matter. Three things before we address the thing I already said. The relationships among things are extremely important in science, right? We kind of have nouns, like concepts of science, and then the way that they are related is kind of like verbs. And so we talk about matter and energy. And how are those two things related? Well, it's a very intricate relationship. When I say the word relationship, you know what I'm talking about, right? Like that, the way that they interact. You have relationships. Not you necessarily individually, but y'all have relationships among each other, right? What is the relationship like between Cameron and Aiden? Well, I don't know. I mean, I don't know the fullness of it, but you know something about it, right? The relationship is the way that those two, in this case, guys, interact. The relationships between the states of matter and their causes and effects is what we're going to talk about today. And then the next thing I want to talk about, so that's about relationships, which are very important in science. And then when I use the word, this is kind of an English note, but when I use the word among, why would I say that? Because I said between just now, and when Streety was reading the objective, he accidentally said between. Why would I ever use this word among? The cause and effect relationship among states of matter. What's the difference between among and between? Do you know? You should know. Among us, yeah. Why is that not between us? Okay. Yes, because you're getting almost there. Between is between two things. So maybe the relationship between you and your mom, or you and your homie, or you and your girl, that is between two things. But we're not talking about two things, so we use among. If it's more than two, we use among. The relationship among your family members, assuming that there's more than two of you, is because there's more than two of you. The relationship among states of matter, because there are more than two states of matter. And the third thing, when we say states of matter, so let's actually write this over here. We said arrangements of matter. I'm going to put that as states of matter. These are different ways that matter can be arranged, as I said, but these are the states of matter. We sometimes call them the phases. The phases of matter. I will use these two interchangeably. You can and probably should also. Your book uses these two interchangeably. States of matter and phases of matter. I've titled it Arrangements of Matter. And how is that related to those things? Well, that's what we're going to talk about first, which is one of your vocab words, the kinetic molecular theory. Or your book calls it better, the kinetic theory of matter. I don't know, maybe the old way that we talked about it was the kinetic molecular theory, but that narrows it down too much into what are like molecules, which is not really what everything or maybe even most things are. And so we now usually call it the kinetic theory of matter. I believe that's what your book calls it. The kinetic theory of matter. Kinetic meaning what? Pertains to? Not motion. Yep. Pertains to movement or motion. Theory, we really do have to talk about it. So you use that word a lot, or you're aware of that word. But remember that in science, theory does not mean just a guess or an idea. It means an explanation that encompasses all of the available evidence. So the kinetic theory of matter is an explanation of the way, we already have talked about the definition of matter several times, but basically it's an explanation, an all-encompassing explanation. It really is exhaustive. That means that it takes all of the evidence available and explains how matter moves, the kinetic theory of matter. The way that we use theory in science is completely different from the way that you use theory in your daily life. It's almost the exact opposite. When you say theory, you probably mean hypothesis. Like if you say, I have a theory that Zach's sleeping because it's his birthday, you really mean hypothesis. It's a guess. The evidence doesn't necessarily support that. There's a little bit of evidence, but all of the evidence in the universe doesn't support the hypothesis that Zach is sleeping through his birthday. In science, a theory means that all of the evidence comes to this conclusion, this explanation. It's an all-encompassing. So we have theories like the theory of evolution is not just, as some people say, a guess as to the way it might have happened. It is all of the evidence about the way biological changes have occurred throughout history that we currently have, explaining the way biological things change. So the kinetic molecular theory is made of at least three tenets. One, you should know these from your vocab probably, or at least from your book. What's one tenet of the kinetic molecular theory? I'll give you a sentence frame. All matter is composed of, what do you think? Atoms. Yeah, that's the right answer. I'm going to put small particles because I think that's what your book does, and because while it's true that it's composed of atoms, sometimes the atoms are bonded together to form molecules. Sometimes they are giving and sharing or giving and taking electrons to form formula units. And so it's more accurate. It's broader but more accurate to say small particles, which could include molecules. All matter is composed of small particles. I'll give you another sentence frame. Those particles are in what? If we're talking about the kinetic theory of matter, those particles are in constant random motion. And finally, what? Those particles, since they're in constant random motion, I don't want to give you that word. What verb? If they're always moving around, what is eventually going to happen sometimes? Collide. Those particles collide. These are the tenets of the kinetic theory of matter. And that relates to the states of matter. One of the ways that relates, maybe a corollary to this, is that faster particles have more energy, and vice versa. If we add energy to particles, the particles move faster. And if the particles are moving faster, they have more energy. They go together. So that's a corollary. It's not actually, it's not number 4, it's as I say, a corollary. It's a effect, cause and effect. It's an effect of these three tenets of the kinetic molecular theory, or the kinetic theory of matter. Faster particles have more energy. Also, more energetic particles with more energy, have more space between them. If I'm talking about faster particles have more energy, what kind of energy is that probably? That we already learned about once this year. Kinetic. And if I'm talking about that more energetic particles have more space between them, what kind of energy is that, do you think? Potential, yeah. So the more energy we give to particles, the more they increase in potential and kinetic energy. They move faster and they get farther apart. When we measuring the kinetic and potential energy of particles on average, that we have a name for that. If we remember, atoms are very, 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 very small. I should say the small particles that we're talking about are extremely small. I like this analogy because it's nice and easy to visualize. That if you have an apple, have you ever had an apple? Yeah. Yes, the answer is yes. So imagine you have an apple. Close your eyes and imagine it right now. Imagine you have an apple. Yep, that's not how you eat an apple, but that's one way you can imagine it. The size difference of that apple compared to the whole world, the entire earth, is almost the exact same difference as that apple compared to the size of an atom. So the apple to the earth is the same as the atom to the apple. So think about how many apples could fit in planet Earth. That's basically how many atoms make up an apple. And so they're very, very, very small. And if we were to measure how fast those particles are moving on average, because they'd have different speeds, right? Even if they're generally moving faster with more energy and generally moving slower with less energy, they would have different speeds. So the average motion and distance between those particles has a name when we measure it. What do we call that? You should know from your vocab.
What is the...
Give me a second while we answer this question, then I'll answer yours. What do you think? If we measured basically how much energy those particles have as they move around, what would we call that? You did it in your lab. I think you might have done it in your lab, at least in a way. What? How did we measure the energy of those particles in your lab? Temperature. Exactly right. Temperature. So you should write that down. And when I say in your lab, Mason and Corbin, when you touched the bottom of that thing, you could tell which of those two flasks had more energy. The one that had made the carbon dioxide or the one that made the hydrogen? Yeah, you could tell because it was warmer. You didn't actually like Joe did use a thermometer to measure the temperature, but you could tell the warmer one had more energy. That chemical reaction released energy, whereas the one that produced the carbon dioxide absorbed energy, lowering the temperature. Streety, you had a question. Measuring kinetic and potential energy of particles on average is called temperature. That's how we measure the energy of particles. And that relates back to, this is now looking like a crazy person, states of matter. That's what we're going to talk about next. What are the states of matter? Let's list them in order. There are 3, and I'm going to put 4. There are more than 4. But let's list them in order from, for a given substance, lowest energy to highest energy. So for a given substance, think about water. If we remove as much thermal energy, if we remove as much temperature, in a way, as we can from that, what state of matter would it be in? Solid. If we add a little bit more energy, that would become liquid. When I say add more energy, that to us would look like warming it up. Add more energy, it would become a gas. And does anyone know the 4th one? Add even more energy, it becomes, do you know? Say it. It's in your, it was in your vocab. Plasma. So this change from solid to liquid, I guess we could use green. You know what that's called. What is that called? We're looking for verbs now. Relationships. The relationship from a solid becoming a liquid is called what? You know what it is. If I take this solid and I change it to a liquid, yeah, melt. Melting. What about liquid to gas? There's a couple different names. Boiling is fine. What's the other one? Yep, evaporation. And then you don't know this one, but it's ionization. Basically, if we give enough energy to a gas, the subatomic particles, not just the atoms, but the electrons remove themselves from the atoms, from the nuclei. That's called ionization. And then that's what happens if we give it enough energy. The sun is mostly in the plasma state. This is on your test. You should write this down. Most of the matter in the universe is in the plasma state. Why? Where is most of the matter in the universe held? Not in our sun just, but in stars. Stars. Most of the matter, by a vast majority, at least of the observable matter that isn't dark matter and dark energy, those ideas, by the way, of dark matter and dark energy are kind of being overturned here in the latter day. But most of the matter, the observable matter that we can see in the universe, is held in stars, and those are in the plasma state. Most of the matter is extremely high energy in the universe. Now, going back down the list, I'm going to do this in a different color. What would we call it if I'm going to erase these pinkies. If a plasma then becomes a gas again? If this is called ionization, what do you think it's called when a plasma becomes a gas? Deionization. This color is not easy to see. What if the gas becomes a liquid? You should know that word too, probably. Condensation. And what if a liquid becomes a solid? Freezing. We sometimes, depending on what's happening, we might call it crystallization also, but they not the same thing, but they get at the same thing. Now is the time of the lesson when we take a drink of our coffee. But also, when we move to talking about these specific states of matter. Really, the only thing, I'm going to erase this kinetic molecular theory stuff down here. I'm going to leave up solid, liquid, and gas. Let's start with solids. The specific things to talk about for solids, I would say pretty easy. We talk about, what color? Brown sounds like a good color for a solid. Oof. Solids can be crystalline or amorphous. Solids can be either crystalline or amorphous. Crystalline means it has a repeating pattern. You know what a crystal is. Yeah. Well, I already started writing, I'm going to hide it. What do you think amorphous means? If crystalline means it has a repeating pattern, what might amorphous mean? No repeating pattern. Random. And when I say a repeating pattern of what? Atoms, yeah, the kinetic molecular theory, the small particles. Doesn't have to be atoms, but small particles. So solids can be either crystalline, if we look at them on the atomic scale, which we can't look means a different thing, but the characteristics they have because of their atomic arrangement is due to their repeating pattern. And for amorphous solids, because of their lack of repeating pattern, okay? Questions about that? I think that should make sense, and we talked about that when you were in 8th grade, so I'm going to move on. Liquid seems like a blue color, so I'm going to do liquid. For liquids, the one I want to talk about the most is Archimedes' principle. And Archimedes' principle applies to more than just liquids, but we talk about it mostly with liquids. The story is that a man named Archimedes was taking a bath. This is in ancient Greece, or maybe I should say classical Greece. I think it was in 300 BC. I don't actually know. Comments are disabled for this video, but look it up on your own. A man was taking a bath in classic Greece, and he noticed, he had been working on this problem for a while about how the interaction between matter and water, matter that went into water, what would happen. And he got in the bathtub, and he watched the bathtub level rise. You've probably noticed that too. I don't know how your bathtub works, but at our bathtub, at our house, the bathtub has like a second drain so that if it gets too full, it doesn't go all over the floor. And you fill it up to the bottom of that drain, and then you get your big meaty body in there, and the water level rises above the level of that drain, right? You've displaced the water, we say. Displaced fluid. You've displaced it. You have replaced some of the fluid with your own body. And the story is that he saw that happen, and that helped him figure out the problem he was having with this. How does that work? And so he jumped up naked out of the bathtub and ran down the street saying Eureka, and then Eureka means I have found it. And that's the myth about how he developed this principle, is that everyone thought he was crazy because he was running down the streets naked shouting, I have found it. And we still call it after him, Archimedes' principle. That something going into the fluid will displace the same volume of that fluid, and that gives us buoyancy. You've heard of buoyancy, but buoyancy is basically the force exerted by the fluid on something that's within the fluid. Like in Streety's lab, things that are denser displace more of the fluid, right? For their volume, they displace a smaller amount of mass of the fluid, so they sink. Denser things sink, and lighter things or less dense things float. And that's the test. If something is denser than the liquid or the fluid, by the way, fluids can be either liquid or gas. The physicist, your doctor, when he says drink more fluids, he or she says drink more fluids means only water, probably, maybe juice. But the physicist, the fluid is anything that flows. So liquid and gases are also fluids. But when an object is in a fluid, it displaces that amount. And if it has more mass than that similar size of that fluid, it will sink. And if it has less mass, which is called density, less mass per volume, density, it will float. That's called buoyancy. We also talk about Pascal's principle. And very briefly, Pascal's principle is just, trying Trying to look for something that I could really easily apply Pascal's principle to. Oh, here's one. It's kind of expensive stuff, but it's all I have right now. If I squeeze this fluid here, you can see I'm not gonna do it because it's expensive, like I said, but what would happen if I squeeze this hard enough? Yeah, because even though I'm not putting pressure up, I'm putting pressure on the fluid, and if I put enough pressure on it, that pressure goes throughout the fluid, and it will go, even though I'm not pushing up, the pressure exerts throughout the fluid. That's Pascal's principle. Pressure applied to a fluid is exerted throughout the fluid. The classic example of this is that if you squeeze toothpaste tube, the toothpaste goes out the end. Even though you didn't push it that way, pressure applied on a fluid is applied throughout the fluid. And then this is where the math comes in. We're going to talk about gas. What's a good color for gas?
Green.
Like fart. Don't say the word fart on the internet. Disgusting. We at your, I don't know, level, that makes it, oops, I spilled some coffee on my book. Your level makes it sound kind of like I'm being mean to you, but at your level, this is what we talk about. We have a worksheet about this, which I already gave you, I believe. Is that correct? We talk about Boyle's law and Charles's law. Charles's law. These two things relate pressure, volume, and temperature of a gas. The way I remember it, you might think this is a bad way, but I'm going to give it to you anyway. Boyle's sounds like it would be about temperature, like it would be about boiling, and it's not. It has no temperature in it. Boyle's law is pressure and volume, the relationship between pressure and volume. Initial pressure, pressure 1, times the initial volume, volume 1, is equal to the quantity, the product of the after pressure, pressure 2, and the volume 2, the after volume. So you can see, what are we always going to have to do with this equation? Every single time, because of the way it's set up. You're looking for a different word. What did you say? No. What did you say? No. There's a step that we only sometimes do with equations that you're always going to have to do with this one. Manipulate. Why? Because you can see it has two terms on each side, right? So we can only, the way we do our algebra in this class, we only can solve for one term, and so you're always going to have to manipulate this one. Okay, this one's really easy to manipulate. Charles's law, not so much. Charles's law relates the volume and temperature. So the quotient of volume and temperature, 1, is equal to the quotient of volume 2 and temperature 2. We won't do the math with this on the board, but that's what your worksheet is for. We'll talk about this more tomorrow as you're working on them. Will you always have to manipulate this one? Yeah, and it'll be tricky because there's one term that's in the denominator. The only other math for this chapter kind of relates more to Pascal's principle, and it was, I'm going to go back to blue, I kind of forgot this. The other math for this chapter is this equation, pressure equals force divided by area, which we'll talk more about tomorrow too. And then, of course, that equation, pressure, relates to the pressure in Boyle's law. Conceptually, and this will be the last thing before we go, but conceptually, Boyle's law is effectively that if you have a balloon, which I wish I had the foresight to bring a balloon, and you put more pressure on it, the volume decreases. A balloon of gas, I should have said that, but you put pressure, increasing the pressure on a balloon decreases the volume. And Charles's law is that increasing the temperature of a balloon increases the volume. You might remember this from when you were 5 years old in 1996, stopped at the Walmart in Scotts Bluff, and there was a balloon in the back seat, and it was the middle of July, and you went back to your car after being in Walmart for an hour or so, and the balloon had popped, and that made you really sad. Remember that from when you were 5 in 1996 at Walmart? And that's when you learned about Charles' law, that the higher the temperature of a gas, the more volume it takes up, to the point that it will pop a balloon.